Section 5.4 is heavy in some skill work in working with integrals. So this may be a video where you want to follow along and pause as we go through the examples, try them yourself. It's really important that you understand the content of this video. So first, before we get into the technique which we're going to learn, which is called u-Substitution, I want to make sure you're clear on the two different types of integrals and what they mean. So in this first box, you see I have an indefinite integral. Anytime you don't have limits of integration on your integral, it's called an indefinite integral. And you can see here that the integral for x squared dx is x cubed over 3 plus the constant. And we've talked about this in previous sections. So really here, when you're finding that integral of x squared, you're finding the family of antiderivatives of f of x equals x squared. Remember, the x cubed over 3 is the basic antiderivative, and then there may or may not have been a constant, which creates a family of antiderivatives. However, when you have limits on your integration, then it becomes a definite integral because it represents a definite shaded area. So you can see here the work that you would go through, and the important thing here is the result is actually a number, and that numerical value represents the area under the curve. In this case, the curve is f of x equals x squared from x equals 1 to x equals 2. And that's why it's a number, because it is representing the value of a specific area. So hopefully that clarifies the difference between the two types of integrals. Next is a table of basic antiderivative formulas. These are things you should be roughly familiar with. You wouldn't have seen them in this particular fashion. However, you learned all of these as derivative rules, and now they've just sort of been reversed. For instance, you should know that the derivative of e to the x is e to the x. So to go in reverse, if you integrate e to the x, you get e to the x back again. You should know that the derivative of sine is cosine. So if I want to integrate cosine, I get back sine. So these are all just the derivative rules that you had memorized, but the order of them has been reversed. Now down here, when you get to these integrals, please understand when you see the dx in the numerator, that's equivalent to writing it this way, where you keep a 1 in the numerator of your fraction and you put the dx at the end. It just saves space by taking this dx and moving it into the numerator. Arc sine and this notation for inverse sine, they both mean inverse sine function. I think nowadays most people use this notation for the inverse sine, but arc sine can be used as well. So just so you know. So these are basic antiderivative formulas that you should memorize. All right, now before we get to u-Substitution, I want to make sure that you remember what the chain rule for derivatives is. When your function is actually a composition of functions, you're going to recognize it is because when you look inside the parentheses at the argument, you're going to notice that in and of itself is a function of x, as opposed to me just having the function sine of x. If your argument's just plain old x, then you go about your business and take the derivative the usual way. But when that argument switches from being x to being a function of x, you now have a composition of two different functions. You've got this function on the inside and the sine function on the outside. That's the time that we use chain rule. In order to take the derivative, the chain rule, I wrote it out in words here. It says first differentiate the outer function. So outside the parentheses, we have sine. The derivative of sine is cosine. Leave the inner function alone. Then multiply by the derivative of the inner function. Most often students won't take the step of writing, I'm going to take the derivative of this. Most often you would probably just go ahead and take that derivative. So the derivative of x squared is, of course, 2x using power rule. The derivative of 2x is 2. And that would be the correct derivative. Very often we pull this algebraic portion out in front. Okay, so that's just a quick recap of chain rule. Now we're going to learn about u-substitution, which is a way to integrate a function whose derivative used the chain rule. So this looks quite messy, okay? And so I'm kind of going to avoid giving you the whole u-substitution thing entirely in symbols. Here's the steps that you need to know and follow. And of course, the best way to understand them is to work through many examples. I'm going to do quite a few with this. U-substitution is called that because you substitute in a function in terms of u that makes your integral simpler. Okay, these integrals look pretty complex compared to what we've done so far. So u-substitution is going to write it in terms of a simpler function. You're going to integrate with respect to that similar function, and then you're going to substitute back again your original function. Your textbook does show a few selected examples, but I'm going to do quite a few more because this is one of those things that you need to do enough to build up your confidence and get good at it. So we're going to integrate these integrals by u-substitution. Now, u-substitution is not going to work on every integral. We're going to learn a lot of different techniques, and you'll have to learn when to try which technique. All right, we're going to do some examples, quite a few of them. Your book does a few select examples, but I kind of wanted to do more than that because this can take some time to get good at. And I'm giving you some additional advice here, which will make sense as we start to do some examples, that you look for a u function whose derivative will match up with the other parts of the function. And typically, to find your u function, you look inside parentheses and under radicals. So if we look at the first example here that I'd like to do, you can see we have parentheses. And so right away, you want to focus on the function inside the parentheses, okay, which is what this second helpful hint was telling you. And it says, look for a u function whose derivative will match up with other parts of the function. So I'm going to take what's in the parentheses and call that my u function simply by putting a u on one side and letting u equal the stuff inside the function. The next thing you will do automatically is you will take the derivative of function u. Now, if I take the derivative, x squared becomes 2x. The constant's going to disappear, and you'll always put a dx on this side. Now, what we mean by will match up with other parts of the function is now I have highlighted in yellow that the yellow portion is going to be equal to u. I'm going to change my highlighter color. And now notice du is the same as 2x, which is here, and dx, which is here. So notice now I have highlighted just about every single part of my original integral, with the exception of this fourth power here. So that's what we're talking about when we say you want the derivative of whatever you choose your u to be to match up with the other parts of the function you're trying to integrate. I'm going to rewrite this integral in terms of u. We're going to look inside the yellow first. The stuff I highlighted yellow is u. I'm going to put u here and then put the fourth power on it. The fourth power is something we can easily integrate. So u to the fourth is the same as saying x squared plus 1 to the fourth. Now 2x dx right here is equal to du. So now I put a du here. And you can see I've now created a much simpler integral. U to the fourth du is very easy to integrate. So I'm going to do that next. U to the fourth, we're going to make it u to the fifth divided by 5. And we're going to put a plus c on this because this is an indefinite integral. So this is the family of antiderivatives. this would be your answer in terms of u. The last step is to go back and swap out the u and replace it with the function in terms of x. So u is equal to x squared plus 1. I keep it to the 5th power. I keep it over 5 with a plus c at the end. And that's your first example. So now that we've got that first example complete, let's just look at it one more time. You begin by identifying a u, and usually your u will be what's inside parentheses or under a radical sign. You write your u, then you take the derivative of u, and you check to see that it matches the remaining parts of the integral. If it does, you rewrite your original integral in terms of u, integrate that, and then substitute back again what u is equal to. Okay? So this gets to be pretty routine once you've done a couple of them, and the important step is identifying the proper value for u. If you do that, then everything else just kind of falls into place. So let's take a look at this next example. Now, as our helpful hint said, we want to go look inside parentheses and under a radical. All right, I've got a radical here. So probably my suggestion is going to be that you let u equal x cubed plus 1. Now I take du and hope it's going to match the rest of the integral. So du, take the derivative of x cubed, we get 3x squared. 1 is a constant whose derivative is always 0. We put the dx at the end. So now we just double check our matching. I have my u value is this. I match this 3x squared appears here. This dx is here. So again, the only thing that is not highlighted is the actual square root function, but that is something I know how to integrate, so that's okay. Now, before I write my simplified u integral, I'm going to go ahead and rewrite my original integral using fractional exponent notation. So remember, a square root is really a 1/2 power. I'm going to, again, just apply the highlighting. I think the highlighting is helpful for keeping track of where different parts are coming from. So here, here. All right, so this is going to be my correct u and du. Now I write my integral in its simplified version. So it's the integral, start with the u. This is u to the 1/2 power, u to the 1/2 power. The 3x squared and dx are equal to du. So I can kick out both of these blue portions and turn that into du. Now I find the antiderivative. I add 1 to my exponent. And remember, instead of dividing by 3/2, we put the reciprocal in front. And then we put a plus c. Now that the integration step is done, I'm going to just substitute my original u function back to give me a function in terms of x's. Now, one last note about the notation here. If your original function is given to you in terms of being a radical, you should give the answer back as a radical as well. So in other words, I switched to the fractional exponent because that helps me integrate, but then when I'm done, I really need to switch the fractional exponent back into a radical. So that looks like this. The 2 is the bottom part of the fraction. That's the type of radical this is. So we have x cubed plus 1. The cubed would stay on that, plus c. And there's your answer. All right, let's look at some more examples. Now, again, I will start to pick up the pace at a certain point, and remember though, you always have the ability to kind of pause the video, figure out what's going on, and then continue. All right, so for the integral in letter C, I'm going to look for my u function. Now here, my parentheses are here, so I should kind of think, okay, maybe this is my u. you need to remember the derivative of tangent. And derivative of tangent, if you don't remember, does turn out to be secant squared of x dx. So going back to my highlighter, I kind of play that matching game. Okay, so I have tangent of x is my u, so that matches. Here's my secant squared x. Perfect, it matches. Dx, it matches. Perfect. I kind of enjoy that about these, that you can match up the parts and kind of get a sense that you're on the right track. Okay, so that's going to be my u and my du. I'm going to write my simplified integral. So this stuff here is just in parentheses. There's no exponent on it. So that's just u. Both of these blue parts are equal to du. So this is a very simple integral. We integrate that. Now substitute back the original value of the u function. One note about how this is written. The way I've done it here with the tangent of x and then the squared on the outside is not typically how we write it. When we're working with trig functions, it can get confusing having this squared so close to the angle. So we usually instead favor this notation where the squared is put directly after the function name before the angle. So the final version here is better notation. I'm going to begin the same way. I'm going to identify my u function by what's on the inside. I take the derivative of u. Derivative of 5x is 5 dx. I go back and I'm going to say, okay, so this part matches this, 5 and a dx, and a 5 and a dx. Okay, so everything matches here except for the cosine. But that's okay. Cosine is a function that I know how to integrate. It's one of the basic rules that you need to have memorized. So it's okay that that didn't match up with anything. So now I'm going to rewrite my integral. U is on the inside of cosine, so this becomes cosine u. The 5 dx, this and this is the same as du. And I need to have my integration rules memorized. The cosine of u becomes sine of u as the antiderivative. So this becomes sine of u plus capital C. And I substitute back my original u function in terms of x, which is 5x. And that's my answer. So hopefully you're starting to get the rhythm of this. We're going to do a couple more. Now here again is where at this point I would encourage you to kind of pause the video and try to start the next couple on your own and see if you can do it. All right, so I'm going to highlight what's in the parentheses because that's my best guess as to what my u function should be. I take the derivative of u. Use my highlighter to make sure everything matches up. So these two parts match in yellow. All right, I've got x and dx and dx. Now there's one problem. If you notice, this 2 does not appear in the integral. So our matching isn't perfect. Here's what we do in that situation. I have x dx in my original integral. So I want to get x and dx by themselves. In other words, I want to move this 2 to the other side of this equation. So that would involve dividing by 2, but instead of writing it as dividing by 2, instead we write it as the fraction 1/2 in front. Multiplying by the fraction 1/2 is the same as dividing by 2. And now you can see that everything on this right-hand side, x dx, matches. So what's going to happen this time is when I match x and dx, I'm going to get rid of those. It will be replaced by this whole thing. I'm going to have to introduce a half du. So let's do that. All right, so I have my integral. Start with the yellow here. So the yellow stuff is u. The squared goes on the outside. Now the x dx is equal to a half du. Now, because when you multiply by a constant, the integral doesn't change. So we usually put that right out in front of the integral. and then put the du at the end. Okay, you don't need to keep the 1/2 on the inside. You can kick it out and just multiply your final answer by that 1/2. All right, now from here, you should be able to take it the next step, which is to find your antiderivative of u squared. And in terms of cleanup here, you should be able to multiply these fractions together. So 1 times u cubed, numerator times numerator is u cubed. 2 times 3 on the bottom is 6, plus c. Once you have it simplified, go ahead and swap back in what u is equal to. Let's try the next one. I begin by identifying the function under the radical as my best guess as to what the value of u should be. I now do my matching and make sure pieces all match up. So I have a dx, which matches a dx. I have an x squared, which matches an x squared. But then I've got this 2, and here I've got a 3. Okay, so first you want to do what we did in the last one. I don't want this 3 here, so I'm going to go ahead and move it to the other side, and instead of writing it as divide by 3, I'm going to do it as multiplying by a third. Okay, so that gets me to this step. Now I have the x squared, which matches the x squared. I have the dx, which matches the dx. I need a 2, though. Well, I can introduce a 2. I can choose to multiply the right side of this equation by 2, and that way this whole right side matches up with everything up here. But of course, with equations, what you do to one side, you need to do to the other. So 2 times a third is 2/3 du. This 2 I'm just going to bring out in front. And now when I go through and check my matching parts, I've got dx, dx, x squared, 2, and 2. So this is the correct u-substitution. I'm going to go ahead and rewrite my original integral because it had a radical. All right, so it's time to write the equivalent u integral. So I start with the yellow. I'm going to have x cubed plus 2 be u to the 1/2 power. The 2x squared dx is equal to 2/3 du. 2/3 goes out in front, du goes at the end. All right, now I take the antiderivative of u to the 1/2. Now, just to be clear, the reason I've got 2/3 sitting there is one is here, that was the constant multiplier, and the other one is the result of dividing by 3/2 is the same as multiplying by 2/3. Final step, I'm going to go ahead and multiply my fractions here. 2 times 2 is the numerator of 4. 3 times 3 is 9. U to the 3/2 plus c. All right, and then as we said before, it is preferred then that you would take that and get that back into a radical form, as well as substituting the value of u. Since the denominator of this fraction is 2, this was a square root function, so it's 4/9 of the square root of x cubed plus 2 cubed plus c. That concludes our look at basic u-substitutions. The more you do, the better you're going to get at doing it.